So we've been looking at improper integrals, and we were actually going through and doing the integration by fundamental theorem of calculus. And if that limit existed, that was what we said the limit was, or the integral was equal to. We said it was convergent. If that limit didn't exist, we said it was divergent. Now, one problem is as you know, functions don't always have antiderivatives. So we can't always apply the fundamental theorem of calculus. So at that point, you'd have to do some approximation method, like you've seen in the past, Simpson's rule, trapezoid rule, something like that. The problem is since this is going to infinity, your approximation would just have to stop at some point. You'd have to use, maybe go out to 100 or 1,000 or 1,000,000, but you'd have to tell the computer to stop adding up those rectangles or trapezoids or whatever after some point. And the problem is if that integral is divergent, your computer's not going to know that. It's just going to add up those areas till it gets to 1,000 or 1,000,000 and then stop and say that's the approximation. What we'd like to know first is there even an answer? So that when the computer adds up those little approximations for a while, that at least it's getting closer and closer and closer to the actual value, as opposed to just diverging off to infinity. So what we'd like to do now is try and determine whether an improper integral converges or diverges, not directly by integration, but by comparing it with something we already know. And typically it's going to be that reciprocal power function that we looked at, 1 over x to the p. So the first thing we'll look at is just comparing the size of those functions, what's called the direct comparison test. So first of all, we want these functions to be continuous, starting at some point and then going to infinity. And there's sort of a sandwiching going on. It's not sandwich theorem, but we want one function to be trapped between the x-axis and another function. So f of x needs to be greater than or equal to 0, but less than or equal to g of x from some starting point to forever. So what the theorem says is something that I think is pretty much intuitive. If, let's say, number 1 there, let's say that the integral from a to infinity of g of x converges. That means that, and you can think of this as area, right? Because in the statement of the theorem, we're talking about positive or non-negative functions. So think about what happens as you take that b to infinity. That means you're getting more and more area, but it's converging to some value. So, so let's just give it a value. So let's say, so for number 1, let's say that the integral from a to infinity of g of x actually equals some value s for some. Well, now think about the integral from a to anywhere you want to stop on f. So any b value. The integral from a to b of f of x dx has always got to be less than s, right? S is the total area under g if you go from a out to infinity. F is even smaller. So if I stop anywhere along the way, the total area I've got so far is less than s. And because f is positive, I also know something else. I know this is positive. But more important is I know what happens as b gets larger and larger. As b increases, that integral increases. Right? Think about it. The area under b is just growing. As I keep moving b out farther and farther and farther, the area under b, or excuse me, area under f, is just getting larger and larger and larger. But it can't get large without bound because it's less than S, or the area under G. So you have this quantity that's growing and growing and growing, but it's got a ceiling that it cannot pass. So this has to converge to something. It doesn't necessarily converge to S, but it can't ever go past S, and it's constantly going up, so it must converge to some value. So as b goes to infinity, that must converge. A more simple way of thinking of it is, say the area under G is 5. Well, F is smaller, so it surely is not infinity underneath F. It has to be some finite amount as well. Okay. What about the reverse? What about, let's say we're looking at 2 there. Say that, now let's start with F. Say we know that the integral from a to infinity of F diverges. Well, it diverges in a very specific way, right? Because it's not negative, this is still, where is it? This is still true, right? This is constantly increasing. But now it's diverging, so it must, the area under there is getting bigger and bigger and bigger. It's growing without bound. It's going to infinity. So since F is greater than or equal to 0, we know something more specific than that. We know the limit as b goes to infinity there, that actually equals infinity. But at any step along the way, stop here at b, the integral from a to b of g is larger. So at any step along the way, the integral from a to b of g of x is bigger than the integral from a to b of f of x. But as I let b go to infinity, this thing's going to infinity. And this is even larger, so it must go to infinity. And that's the definition of being divergent, right? So again, more simply, if the area under F is infinite, the area under G is even larger than that, so it's just more so infinite. So, so what we're going to be looking for is doing these kinds of comparisons. If we have something that we're trying to figure out if it converges or diverges, if we can argue that it's less than some integral that converges, then we can argue that it converges. Or if it's bigger than some integral that diverges, we'll argue that it diverges. So this is how we'll use direct comparison, by directly comparing the size of those integrals. And we'll look at an example of that.